right, everybody, let's get started. Good afternoon, everyone. Welcome into the North Carolina Museum of Natural Sciences. Welcome to the SCCU Daily Planet Theater. My name is Chris, and I am your host for the Lunchtime Discovery Series. Every Wednesday at noon, we gather here inside the museum, inside the globe, and around the glow of the museum's YouTube channel in order to hear about what's going on in North Carolina around science, nature, conservation, education, art, and more. The folks over in the Office of Environmental Education and Public Affairs within the Department of Environmental Quality do the fantastic work of finding incredible speakers, great people to come inside the museum or join us online, share with us their knowledge, their insights, the things that they are interested and know a lot about. And then we get the opportunity, one, to learn what they know a lot about, and then the chance to ask questions as well. So, thanks for joining us online if you're watching on YouTube, or for being here inside the museum. You can grab a seat on the first, second, or third floors for today's presentation if you'd like to join us. And then if you're watching online, I'll remind everybody, make sure that as we go throughout the presentation, as you have questions, thoughts, insights of your own, drop those there into the chat box. We have people standing by on the lines who are monitoring the chat. And after the presentation, we'll be able to share your thoughts and questions with today's guest speaker. That way we can have a great conversation about today's topics. Now, for today's Lunchtime Discovery Series, the last installment of our Earth Month series, where we've been hearing stories of investing in people and places and investing in the future for the planet, I'd like everybody to meet a Ph.D. student at North Carolina State University, Rebecca Composto. Rebecca is working with the Geospatial Analytics Group at NC State University, and here to share with us today a little bit about using maybe the coolest tools out there, satellites and geospatial information systems, in order to help us learn more about floodplain mapping. Everybody, please welcome Rebecca to the stage.
Yay. Thank you. Thank you so much for that introduction, and thank you so much for having me. I'm really excited to be here with you all today. So again, yes, I'm Rebecca Composto, a third-year PhD student at North Carolina State University at the Center for Geospatial Analytics, and I'm in Dr. Tolber's Geospatial Analysis for Environmental Change Lab. And before I get started, I just want to say thank you to the center I'm in, as well as the U.S. Geospatial Intelligence Foundation and the North Carolina Space Grant for funding. Their funding has supported my research, and I really appreciate it. So yes, thanks again for having me. The roadmap for today is I'll be talking a little bit about flooding, and then giving an overview of satellite imagery, and then talking about my research mapping past flood events. And then I'll end, and I'll also touch a little bit on some machine learning topics as well, and try to explain that as best I can. But mainly talking about flooding and how flood maps can help us prepare for the future. And this photo here is a little preview of what I'll be talking about, a flood event that occurred in my hometown of Philadelphia that I'll be talking about a lot more. So just to go ahead and give the main takeaways, why wait till the end? Let's just share those at the beginning. I'm really hoping that folks walk away with this, or from this presentation, with a good understanding of satellite imagery, both the advantages of satellite imagery and also some of the disadvantages, some of the things you should keep in mind when using satellite imagery. I also want folks to walk away with an appreciation that machine learning and satellite imagery together can be a really powerful combination in mapping past flood events. So since it's a lunchtime talk, satellite imagery and machine learning go together like peanut butter and jelly. And if you're more of a desserts person like me, maybe like a s'more. And before I talk a bit more about flooding, I want to talk about my journey to NC State and how I ended up there studying flooding. And since it is Stanley Cup season, I thought I would use hockey as a little visual for how I ended up here. So I grew up in Philadelphia, and I studied biology and environmental science. And I really enjoyed ecology, and I was making maps of different species using geographic information systems, or GIS. And I enjoyed that, but I realized maybe I wasn't so interested in the species and more so interested in the map making. And that's how I ended up doing government contract work in Washington, D.C., And there I got to work with government agencies like FEMA and map out how different supply chains were impacted by different flood events. So maybe after a flood event, how were groceries able to reach grocery stores, gas reach gas stations, how are transportation routes impacted by different disasters? And I really got to dive into that in DC. And after DC, I was still wanting to work with satellite imagery, and that's how I ended up at North Carolina State University, NC State, go Pack, and I get to study flooding at NC State. So I'm sure, as most folks know, flooding can cause a lot of damages and disrupt our daily lives, especially in North Carolina. Flooding can also be a very expensive problem. Globally, it's the most expensive natural disaster. And in the US alone, it costs around $33.9 billion every year. So it's a very expensive problem, but it can also disrupt daily life, closing schools, and causing displacement of people as well. And while flooding is this big, scary problem, there are also solutions for flooding. And some of these solutions can be aided by maps of past flood events. So one way a map of a past flood event can help us is by helping inform zoning and where we build. So knowing where a past flood event occurs can help us learn, okay, we maybe don't want to rebuild in that area that just flooded, and we should limit development and new buildings in that area. And this photo up here on the right is a photo of my dog in Lake Johnson. And so putting this into practice, you wouldn't want to build right next to Lake Johnson because that's an area that is likely to flood because it's near a river or near a lake. Another way that maps of past flood events can help us and are useful is that they can help us request money after a disaster. So after a natural disaster, you can appeal to different government agencies for funding for recovery. And so what you can do with a flood map is you can have your flood map, and then you can overlay something like farmland or critical infrastructure, determine the amount of damage, and then make an appropriate request for funding to repair. So that's another way that flood maps can be really useful. And flood maps can be created a bunch of different ways. One way is by surveying and physically walking around and figuring out the extent of flooding. That's one way to map a flood extent. Another way is to use physics and make a model and predict where flooding occurred. And another way, probably my favorite, is using remote sensing. And remote sensing is just any time data is collected away from an object. So even taking a picture of your phone of a flower, that can be considered remote sensing because you're not just looking at the flower itself, you're taking information from it from afar. Drone imagery is another example of remote sensing, and satellite imagery as well. And satellite imagery is basically we have satellites circling the Earth, they're orbiting the Earth, and they're taking photos from up there, taking satellite imagery. And there are two main types of satellite imagery. So number one, there is imagery that's collected by passive instruments, and those just use the sun's rays to see the Earth's surface. So they're looking down, there's energy from the sun, and they're collecting information using the energy from the sun. The other type of satellite imagery is collected with passive instruments, and those satellites will create their own energy, send that down to the Earth, and then measure the amount of energy that's reflected back from the Earth's surface. And the big advantage of active instruments is that they can actually see through clouds. So oftentimes in a flood event, there's a lot of precipitation, a lot of raining, and a lot of clouds. And active instruments have the advantage that they can permeate those clouds and see through those clouds and collect imagery. So that's a big advantage. And passive instruments, they'll collect imagery and it'll look more familiar to our human eyes because they'll have red, blue, and green and look like images you might see in Google Maps. So apart from those two types of satellite imagery, imagery has other properties as well. There's the source of imagery, so satellite imagery can come from a public source. It can also come from a private source. And one thing I like to do when there's a news story that has satellite imagery is to look at the bottom of that satellite imagery and see what the source is. And oftentimes in a news article, it'll be either from Maxar or from Planet Labs. So those are two big private companies that produce a lot of satellite imagery. And then there's also NASA and the European Space Agency that are two big government groups that also create satellite imagery that is freely available to the public. Another aspect of satellite imagery is pixel resolution. So depending on how big your pixels are, you can get more information from the satellite imagery. Or sorry, how small your pixels are, you can get more details and more information from your satellite imagery. Timing is another important aspect of satellite imagery. And so there are two main ways you can think about timing. Number one is when the image is collected, and number two is when, how often the satellite revisits the same place. So revisit time as well. And again, type of active or passive sensors. And here we have an example of satellite imagery. So on the left, we have a satellite image of a baseball field, and on the right, we have a photograph of a baseball field. So a lot more detail in the photograph, and then we can see the pixelated satellite image on the left. And the source for the satellite image is NASA or Landsat, a Landsat satellite, and the pixel size is 30 meters. And you can also think of 30 meters as the size as a baseball diamond. So that's how big the pixels are. Another aspect of the satellite image is timing. So the satellite revisits each point, so this exact baseball field, about every 8 days. But I don't have a specific date of collection for this image. And this is an active sensor, meaning, again, it's using the sun's rays to collect information. So satellite imagery is composed of pixels, so these different cubes that each have data within all those cubes. So the numbers in these pixels can represent amount of greenness, amount of blueness, and other information that satellites collect. And a model can learn from the amount of these different values and make predictions and classifications of what these pixels are. So a model can learn from these pixels and classify them into land cover, and in my case, flooding. Digging in a bit more to pixel size and what pixel size, how pixel size influences what we can use satellite imagery for. On the far left here, we have some 8-meter satellite imagery, and then the pixels get smaller and smaller. And you can see as the pixels get smaller, you can see more detail. You can see where those fuzzy things are trees. So you see trees and you see more details. And showing another example of pixels going from larger to smaller, we have an image from my study area of Philadelphia, and we have the pixels are 10 meters here on the far left, and in the middle they're 3 meters, so you might be a little hard to tell, but they're getting more, the edges might seem more crisp and more detailed. And then on the right we have our Google imagery that you can find in Google Maps that has a lot of detail and a lot of specificity. So in the context of flooding, satellite imagery certainly has some advantages, and it also has some disadvantages. And I'll start with the advantages. So satellite imagery is considered a very real data source. It's considered to be very aligned with what's actually happening on the ground, as opposed to a physics model that might be predicting or estimating what's happening on the ground. The other advantage of satellite imagery is it tends to have wall-to-wall coverage, so you can study a couple counties or a large area at once instead of a smaller area. And if you are out there on foot surveying an area, trying to figure out the extent of flooding, it would take you longer. You might not be able to reach all the areas that you want to, so this wall-to-wall coverage is really useful. Another aspect or another advantage of satellite imagery is it can be timely, so a model can be performed quickly on imagery to turn it into a flood extent. And it can be collected daily in some cases as well to provide timely information. But there are also disadvantages of satellite imagery. So publicly available satellite imagery, the free imagery that governments make available, might not be available for your specific flood event. So if a flood happens on Monday, the satellite might not visit that area until Friday, and therefore not be able to collect information on the flood event you want to study. Clouds are another disadvantage for some types of imagery. They can block the sun's rays, and then you can't see what's happening underneath. You can't see the data underneath. But for active instruments that create their own energy or send out their own energy, they can see through clouds, again, which is really useful in a rainy event. And also, satellite imagery can't see under bridges and oftentimes cannot see flooding under vegetation. So there's a couple of disadvantages to keep in mind when using and working with this data. So I'll just pause for a moment and have folks think a little bit about what satellite imagery they would want to use. So this is the parking lot across from the Natural History Museum. And let's pretend for a moment there's a flood event and you want to map out the flooding in the parking lot. And option 1 for your satellite imagery is cloud-free, really, really small pixels, but you're going to have to pay, let's say, $200 for this image. The second option is cloud-free again, but this time the pixels are larger, let's say twice the size, but the imagery is free, it's public. Which data set are you going to pick? Give you just a moment to think about it. And the answer is, it depends. Much like much of research, the data you want to use to answer your question, the data you want is probably going to depend on what questions you want answered. So if you want to know really granular information and which cars specifically were flooded, you probably want to use smaller pixels and higher resolution satellite imagery. If you just want to answer a yes or no question if the parking lot was flooded, you can probably use bigger pixels. So yeah, unfortunately, there's no one right answer. It really depends what your science question is for what data to use. And now I'll share a quick example of how satellite imagery can be useful, but also a little imperfect for mapping flood events. So this photo here on the left that we have, this is a PlanetScope satellite image. Planet Labs is a private company that sells imagery, and they have nice daily high-resolution imagery at 3 meters. And the red areas are vegetation, and a little hard to see, but the dark area down the middle is permanent water. So that's before Hurricane Helene, that's that image. And then on the right, we have an image taken slightly after Hurricane Helene. And you might be able to notice that through the middle, that dark flooded, or that dark river area has now become a greenish color and gotten wider. But the main thing I want you to notice from this image is that there are clouds. And clouds are, let's say they're blocking around 40% of the image, but in addition to the clouds, there's also cloud shadows. So really only 50% of this image, or around 50% of this image is usable. That doesn't make this image useless. It can still be useful to see how wide the flood extent went around that river. But there are certainly key areas of the area that were flooded that's blocked by clouds. So just important to keep in mind that satellite imagery can be really useful, but sometimes blocked by clouds. And so the hurricane event that I've been thinking about and studying for the past couple of years is Hurricane Ida. And Hurricane Ida was a Category 4 hurricane that landed in Louisiana, came up to the northeast, slowed down, and released a ton of rainfall. You all might remember that New York City subways flooded. It was a very, very big and in the northeast surprising flood event. And in total, there are around 75 billion, potentially more, in damages. So a very expensive event. And in Pennsylvania alone, there are around $2.5 to $3.5 billion in damages. And when I started graduate school at NC State in 2022, I went looking for a flood extent and a flood map of my hometown of Philadelphia, and I couldn't find one. So I wanted this to be my research project and look into this flooding a bit more, because for such an expensive event, I thought a flood map of where the flooding occurred could be useful for future planning purposes. So in addition to wanting to study Philadelphia, a little bias as where I grew up, I'm also interested in studying flooding in urban areas. In urban areas at the city block level, things change block to block. They just tend to be a bit more complex to map floods, and so I wanted to really test some methods in this area. I also included some other surrounding, slightly less urban counties as well. And it just so happened to be that there was very cloud-free Sentinel-2 or 10-meter satellite imagery available for this flood event. I just demonstrated how that's not always the case. It's almost rare that there's cloud-free imagery available. And the timing of this public imagery was also very well timed. It collected imagery on the day of peak flooding. And before I get into applying a model, a machine learning model to the satellite imagery, I want to take a step back and talk about these terms, talk about these models, and then I'll also show a little example and talk through how these models work. So to start off with, artificial intelligence, that's this big umbrella term. And before I read the definition, just want to talk about those two words individually. So intelligence can be considered anything that a human can do. So maybe learn the rules to a game and play a game. It can also be solve a problem, maybe make a recommendation. That's all things we think about for intelligence. For artificial, when I hear artificial, I think artificial food coloring, so something like red food dye. It's something that's human-made, maybe not found in nature. So the definition for artificial intelligence, putting those things together, is any technique that enables a machine to solve a problem like a human. And machine learning is a subset of AI, or artificial intelligence, and it's a technique of giving data to a computer and that computer learning how to make predictions with that data. So machine learning is a technique, and it's under this big umbrella of AI. And the reason why remote sensing scientists and folks that use satellite imagery bother with machine learning is that the methods of machine learning tend to be more accurate than previous methods of just using maybe one water index or one piece of information and maybe building a model by hand, putting in the different inputs and all of that. Machine learning has been found to be a more accurate method. So it's been really popular, not just in my life of classifying satellite imagery into flooding and not floods, but also classifying imagery into different land cover types and measuring changes in the land cover over time. So now I'll talk a little bit more about machine learning and how this system works. But before we get to the computer side of things, let's just pretend for a moment that you want to teach a kid the names of different fruits. So the way you might teach someone is showing them a picture of a lemon and saying, this is a lemon, a picture of an orange and saying, this is an orange, pomegranate is a pomegranate, so on and so forth. And maybe the kid learns the fruits just by hearing those names. But let's say you also give them a piece of lemon, they try it, they taste that it's sour, okay, now they know a little bit about its taste. They try an orange, and they know the orange is sort of sweet, and they learn the fruits with that additional information. This is pretty similar to how a machine might learn to label different images of fruits. So the machine might see the photo of the lemon, see that it's labeled lemon, and then see the associated information on color, taste, and texture, and eventually learn what a lemon is. And the goal with machine learning is that eventually it'll see a bunch of labeled lemon images, and then eventually you can show the computer a picture of a lemon it's never seen before, and the computer can make a prediction with the associated data about what the name of that fruit is. So what that image is, it can predict that it's a lemon. So that's a little bit about how machine learning works. And there's one type of machine learning that's called the random forest algorithm. I might also call it random forest model. They're both random forest. It's a common and popular machine learning technique that's pretty accurate when classifying imagery. And the way it works is you'll have your unlabeled data. It goes into the model, and it'll go into different decision trees. And within each decision tree, there'll be a couple different pieces of associated characteristics or data that will be used to make a prediction on what that image is. So in tree one right behind me, we have taste and texture. So in that decision tree, the model will see the photo of the lemon, have information on taste and texture, and make a prediction about what the image is. And it might get it wrong. One tree might get it wrong. Multiple trees might get it wrong. And it might say, hey, I looked at the data. I think this is an orange. And then we go to the next decision tree with a couple other features or data associated with that image. And it might have information on taste and color. And now it predicts right, it's a lemon. Another decision tree with different features or data predicts lemon again. And after all those decision trees, there's going to be a majority vote where altogether the decision trees vote on what they think the image is. In this case, overall, voted correctly that it's a lemon. So just as with the fruit basket example, you can show different images and the computer can classify those images, the same thing can happen with satellite imagery and classifying that satellite imagery into flood pixels, water pixels, and not water pixels. And so for the case of my model, again, we have the Sentinel-2 10-meter satellite imagery, which has information on amount of red, blue, and greenness. I also included some other information, like a water index. I included slope information because slope influences where water is pooling. It's an important factor. And impervious surface, since I'm interested in urban areas, I thought impervious surface might be an important data set to include to help the model learn where flooding might occur. So all these data sets go into the model, and the model learns from some labeled pixels what the characteristics are of flood, water, and not water. And then the output of the model is a classified image. So multiple layers of data go in, train the model, and then the output is one layer where some pixels are water, some pixels are flood, and some pixels are not water. And just as there were labeled images of the fruit that the model can learn from and classify fruit, I created some training data for my model by hand drawing polygons, so drawing polygons of known flooded areas so that the model can learn the characteristics of the flooded areas and make predictions based on that training data. And then you also, for the model, leave a little bit of data out to also test the model and find accuracy. So that's an overview of how the model was created, and now we can take a look at some of the outputs of the model. So in the background here, we have that Sentinel-2 satellite imagery, and then the dark blue areas are permanent water, and the light blue areas are flood. So you can see some of that flooding there. And one of the main areas that was flooded after Hurricane Ida was Interstate 676. This interstate runs through the city, and it was flooded. And you can see in this photo over here, it might look like a river, but that's actually Interstate 676. That brown strip down the middle, that is the flooded interstate that runs through Philadelphia. And I was really happy that the model was able to capture that light blue area. That's where the flooding is. The light blue area in the middle, not on the far left, that's Interstate 676, and the model was able to capture some of that flooding. So the model overall had high accuracy, which is great. And it was able to, when tested on some polygons not used for training, it was able to predict accurately where flooding would occur. But something to keep in mind for this flooding, and you might notice something a little bit weird about this map, and that is there are some gaps along the interstate. So through observations and some media, I know that between those two blue points, this whole area flooded. But satellite imagery can't see through bridges, so it looks like there's a gap. So that's another thing to be aware of. As a human user of satellite imagery, you know, if you were using this map to make a decision, you would just want to remember that there might be some gaps due to vegetation and bridges that satellite imagery can't see under. It can't predict flooding under those areas. And so the methods for all of this and the visualizations and the actual flood extent are all available online, and the code is available as well, and the code can be adapted for new areas. So yes, it's all available. And now I also want to touch briefly on another cool model that I did not create, but was a project by NASA and IBM. So NASA and IBM worked together to make this model called a Prithvi model, and this is more so in the deep learning side of things. The model I was using in the machine learning, this is more deep learning. And this model was trained on 1 terabyte of satellite imagery, and satellite imagery from around the globe. Yeah, so 1 terabyte trained on a lot of data. And it's sort of this big model that they then fine-tuned to be able to do different tasks. One task that this model can do is identify wildfire scars after a wildfire on the Earth's surface. Another thing this model can do, and that I'm excited this model can do, is it can classify Sentinel-2 10-meter satellite imagery, the same imagery that I used, into flooding, and it can be applied around the world. So for my model, made for a couple counties in Pennsylvania, trained for that specific area might not apply or might not be the most accurate when applied to a new area, but this model very purposefully can be applied around the world. And so this is an example of uploading a little bit of satellite imagery into the model, which is available publicly and available online. That satellite imagery is in there, and it's loading, and it's about to come out classified. And just for context, so the model I've been working on in my PhD research maybe took around 1.5 to 2 years to make, and this model just predicted the flooding in a couple of seconds. So really exciting model, and yeah, I'm excited to see what this model can do. In the center image here, the white area is water, and the black area is not water. And you might recognize that there's permanent water along the left-hand side, and then those couple little polygons in the middle, that is the flooded Interstate 676 that I showed earlier. So the model was able, this Prithvi model was able to pick up some of that flooding, which is really exciting. So if this is of interest, if you like learning about satellite imagery and some of the machine learning techniques, there is a lot more out there. So NC1Map has some really great data sources, and even in the search engine for NC1Map, there's Imagery. So they know that folks might be looking for imagery in that database. If you're interested in finding your own Sentinel-2 or Landsat or other satellite imagery, NASA Worldview is a good place to visualize and find imagery and also download imagery. And then NASA also has some great webinars and training material called the Applied Remote Sensing Training Program. There's some great things there that I've used and really enjoyed working with. And also, if you ever want to learn more about flooding or get some questions answered about specific flood events, the Center for Geospatial Analytics over at NC State is another great resource, and folks there are definitely happy to answer questions and help out. So just to bring things back to the so what, why do we even bother mapping past flood events, is ideally these maps of past flood events can help city planners, emergency planners, and just everyday residents prepare for future flood events. So again, flood maps can help inform some zoning policies, can maybe help you find alternative transportation routes, and just learn from past flood events and prepare for the future. So thank you so much for listening, and I'm happy to answer any other questions.
Rebecca, fantastic job. Thank you very much. Very cool and interesting work. I'll just say the very first thing, and I've got the chat pulled up on YouTube, so folks, as you download the presentation you just saw and heard, hi YouTube, as you download that information, get your questions typed up into the chat. We've got lots of time for Q&A here, and if you're here in the room with me and you've got questions, remember you can just wave down at me, you've got a question, and we'll call on you wherever you're at, first, second, or third floors, and then you can ask your questions. We'll go to the second floor first.
Yeah, sounds good.
So the question was, our question asker works in real estate and wants to know if you can use this kind of technology for mapping floodplains in use in real estate development.
Yes, well, yeah, thank you so much for your question. Really relevant question, and I definitely think, so I guess the thing about mapping flood events in the past is they're not an average of all flood events. It's just saying this one flood event occurred here, so it might not be able to, looking into the past might not be able to tell you very well what the future of flooding will look like, but it will tell you, okay, the flooding got this close to your real estate project, so that's something to be aware of and maybe something to account for. Mm-hmm. Yeah, good question. I mean, it can't influence whether, FEMA has its own system for insurance requirements and flood insurance requirements. And ideally, I would hope this sort of map can help inform where to put mitigation efforts, maybe green infrastructure, maybe help folks make a decision about how high to put the first floor and that sort of thing. And if you're interested, Zillow now provides information on flood risk through the First Street Foundation, which is an organization working on predicting floods. So Zillow now has a score for how likely a property is to flood available on that website. Yeah, thank you.
Great questions. Others in the room, wave down if you've got a question about floodplain mapping. If not, I'm going to take one from the chat. Paul wants to know, what application are you using for random forest, as in ArcGIS Pro, Grass, or something else?
Yeah, great question. So for the first part of my dissertation, I use Google Earth Engine, which is a platform run by Google. There's a lot of helpful information and tutorials on how to use Google Earth Engine, and it runs pretty fast. And the platform hosts all your satellite imagery. So if you're working with big satellite imagery or a big area, it still runs pretty fast, and you don't have to download that imagery. So that's what I've been using for the first part, and now I'm switching over to using Python.
Now it's getting into the math, right?
Yeah.
Just turning all of the pixels into numbers and straight from the data, right?
Yes, yeah.
Fascinating stuff. Let's see, how do you get elevation information from passive satellite photos?
Yes, so for elevation, I use the US Geospatial, no, not US Geospatial, the USGS digital elevation layer. I think they have one at 10 meters resolution and 30 meters resolution, and that's the elevation layer that I used.
Did you have to go through and classify things like land use types, water, flooding, non-water? I guess you trained your model by going through. What was the resolution that you were using? Was it like the super fine scale Google imagery in order to draw your polygons? Or do you have to stick with the like 10 meter, was it 10 meter? Or 3 meter Sentinel imagery to go into the model?
I'll go back to that slide. Yeah, so for drawing the training data, best practice is if your model is being run on Sentinel-2 imagery or on one type of satellite imagery, that your training data comes from a separate and higher resolution image. And so that's when I pulled in some of that private data from PlanetScope to really make sure the polygons were what I thought they were when I was drawing them. And then I did toggle some layers with Google satellites, and I also had a permanent water layer as well. And then another fun data source I used to look around for this training data is I pulled in some flood-related social media posts and tried to really make sure I wasn't missing some big flooded areas that might be useful for training the model.
So tell me more about the social media data then. Was it just, you just went to Facebook, Blue Sky, Instagram and said, Hurricane Ida in Pennsylvania, and just saw what images popped up, and then you were Google Street Viewing to see the extents? How did that work?
So thankfully, someone else gathered the social media data. There's a group that created a website called Global Flood Monitor. So globalfloodmonitor.org, I think, but I think if you Google those words, you can find the website. And they do the web scraping and have scraped, they scrape Twitter data, which you can't do anymore because it now costs academics money to scrape Twitter. So I think their scraping stopped in 2020, around 2022, I think. But they were able to, since my event was in 2021, I was able to use some of those flood-related tweets, and they had a latitude and longitude, so some information on location that I was then able to look around where those social media tweets occurred. So that star there in the middle is an example of a flood-related tweet that I poked around in that area looking for some flooding or permanent water to train the model with. Yeah.
So the scraping gathered GPS coordinates, and so then you could use that information. Was there, what type of ground truthing did you have to do for your model, or did you do any besides testing with the polygons that, you know, like could you use the social media data and maybe images that people have posted to then also go back and ground truth your model?
I did do that a little bit. So again, yeah, the tweet had, you know, that point location that I didn't just assume that point was exactly where flooding was. So I visually looked in the satellite imagery and looked around there and maybe drew some flooding polygons if it was visual, but I didn't if it wasn't. So I verified the points of the tweets. But then, yeah, sometimes the social media information had an image and a photo of flooding. And that was also really useful to go into different, like if I recognized the street name, I would try to go to that location and verify that the model had picked up that flooding as well.
And hopefully it wasn't somebody making a joke with like a picture of a puddle in their backyard. All right, let me get another one here for you. How much have you studied Helene flooding in Western North Carolina at all?
So my lab with Dr. Tolber and an undergraduate, Darcy Boast, are looking into Hurricane Helene flooding. There's not an obvious path forward because the imagery is very cloudy, but ideally something can be found from this kind of, from this cloudy image. Ideally, some useful information can still come from it.
Fascinating. We've been hearing a lot about Helene here in the Lunchtime Discovery series, and about things like floodplain restoration as well. Do you feel like the models that you've designed and that other research groups are coming up with, like the IBM, the NASA IBM model as well, would be valuable in conservation efforts, restoration efforts, and floodplain mitigation?
I do think so. I think maps of a specific event are really useful for making sort of maybe broad conservation plans. You might want to stack a bunch of maps together instead of just using one specific event, and also add in some other factors and maybe predict into the future. But yes, ideally a map of a specific event with some additional information can be useful for those types of decisions and planning.
Now, what gets a PhD student interested in geospatial analysis and GIS systems?
That's
because I think of it as a tool, but you seem to really have dove into understanding and advancing the tool itself instead of using the tool to answer maybe other bigger questions. And maybe my analysis is incorrect, and you can say so.
No, I think that's accurate. I think the way I got into it is my GIS classes, or Geographic Information System classes, as an undergrad were in a computer lab with no windows and no natural light. I didn't really notice that couple hours passed working on a map, and so that's how I knew I was definitely interested in it. And yeah, it can be a very visual, very almost creative outlet to make a map, and also a math and science thing to also think about the Earth and Earth systems and make a map that way too.
Fascinating stuff. I had some opportunity to, well, I dipped my toe into GIS in school as well, and did not have the same outcomes as it sounds like you had. So I was just curious.
Yeah.
And it's fascinating. Making the maps can be a lot of fun. Taking the math, the science, the data, and then putting it into some sort of the right representation for the information that you want to get across. When you've finished your floodplain maps for the city after Ida, did you have the urge to just send them to city managers and be like, hey, just so you know?
I'll go to this page. I did a little bit, and I think something I'm trying to continue to work on is, I had a little LinkedIn post, and the data is available, but I haven't necessarily done that final delivery piece of trying to get in contact with people who would find this map useful. I sort of have put it out there, but haven't made that final connection to different folks who might be able to use the map. So definitely something I'm working on and want to continue to work on to publicize this and make it useful and better. And another piece of feedback I've sometimes gotten is maybe before sharing this, I could clean things up a bit more and fill in those gaps along the interstate and make things a little more understandable before continuing to share them as well.
How did your model compare against things like the 50, 100, 500-year floodplain maps that FEMA produces and that, like real estate and insurance companies take a look at?
Yeah, great question and a great opportunity for me to plug the paper.
There you go.
The paper does cover how this flood event overlaps with FEMA flood zones. And what I found was, as many other researchers have found, as also in the Center for Geospatial Analytics at NC State, flooding certainly occurs outside of FEMA's 100-year flood zone. It occurs in minimal hazard zones where you're not required to buy flood insurance. So flooding definitely occurred outside of those areas where you're required to buy flood insurance. So yeah, it was definitely occurred outside of those areas, and hopefully that can also help. One of the reasons I wanted to study that is because there is this misconception that if you live maybe right outside a flood insurance zone or a little bit outside of flood insurance zone, you're completely immune to any flood risk, but wanted to add to the big body of research that shows there's certainly flooding that occurs in those areas.
Wow, fascinating stuff. Certainly lessons learned, even here in North Carolina in the wake of Helene, of what the types of information that maps like that can give us, and what it even means for an event to be a 100-year flood or a 500-year flood event, and how that can impact you when you think, well, I don't know, I might not be around for 500 years and have to experience it. Yeah. It could also happen tomorrow. It could be this hurricane season that places, because that was the fascinating thing about Ida and Helene, right, was that these storms have moved so much further inland in the United States than we ever really think hurricanes do.
Yeah, and that's definitely something for a map of past flood extents. They're really useful, and I really like working with them and making them and publicizing them, but they aren't going to be your average risk per year. It's just an example of one event, and flooding can occur in a completely different pattern. And so, yeah, it's important to, I really like these maps. They're important to use, but it's also important to think about overall probability of flooding and not just the past flood events.
Well, Rebecca, thank you for coming out to the museum today. Thanks for participating in the Lunchtime Discovery Series and sharing your work with us.
Thank you so much for having me.
Excellent stuff. Very cool. Glad that there's smart people out there doing work like that, right? I think so. And that they're right up the street from the museum at North Carolina State University. Great partners in so much that we do here at the museum as well. So thank you very much. Excellent job. Everybody, thanks for tuning in today. Thanks for joining us here at the museum. We'll be back here again next Wednesday at noon with another edition of the Lunchtime Discovery Series. If you want to know what's coming up in the future, head to the website eenorthcarolina.org. There you will sign up for the email newsletter for Lunchtime Discovery Series, and then you get this YouTube link in your inbox every Wednesday, every week. That way you just click over, join us, bring your thoughts, questions, insights, maybe learn something new and hear from interesting people. We will be back here next week. They tell me they've got an amazing May set up. And Lisa Tolley is down here just like thumbs up. It's going to be great. They do great stuff over there in the Office of Environmental Education. So thanks for tuning in, everybody. We'll see you again soon. Bye.